load the FastScape and all the libraries we need to. We remove the diffusion components, and then we're going to run one, a model which has this characteristic here, m equals 1, uplift rate of 10 to the minus 3, so 1 millimeter per year, and a model size of 100 kilometers by 100 kilometers. The model function that we're going to put into the model to represent precipitation. And for that, we build the precipitation. We put it to the power m, so it's a time function. We put it to the power m, multiply our coefficient erosion or erodibility, and we build an array which we give the dimensions of time, which will then, like this, compensate from climate for about 10 million years and then a perturbation at a given period. We put that into one thing I realize, I know now why the code was so slow. It's because I'm writing the output to 5. And I figured out actually that if you do that, you might slow down very much the model, because you basically are trying to write the external disk as you do this. I'll remind you that we are in our external driver. We're not inside the container. I think that's a simple way out by saying, look, save the output into the main container much faster. But, just demonstrating it to you that, now it goes very fast as it should go. Nothing which you can also do is you can actually remove this option. So you just run the model like this. You comment out from, and it will even go faster. Okay. Now, for your information, and especially I've crushed Safari. Oh gosh. We'll do it again. This is restart. But Caroline, I was going to tell you, I figured out the reason why sometimes your notebooks don't run, and others mentioned that. Container, there's actually a limited amount of memory that's available. And so if you run many, many notebooks and don't, just builds up, and there's not enough memory, and you crash the container. Okay, so it's not an issue. So what you do is the old one. So again, I'm going to do this now. I will need to rerun very quickly all the. You see, now it's very slow because I forgot to do that. So I'll kill this one. I'll remove it like this. And then we can at the output and notice what we noticed yesterday. I'll read you guys for topography, and if we play the animation, and I'm going to start somewhere here at about after the end of the steady state. I'll need to watch this. Sorry, I need to run it twice because of Zoom. It doesn't always show it. Not in topography, but nothing really major. And we're going to go and see why. A very rapid change. So here it was like 1 million years. Let's make it like of it. Yes. Okay. Oh, sorry. We should see first that my cycles are very short. Okay, they're only 100,000, so they best on this plot, which runs for 10 million years plus something like 500,000 years. I'll run it again, and do much because the perturbation are so rapid that the systems won't have time to respond. So if again I play it, see the drawing. And then as we get through the, you know, the 100, after 10 million years, we start to have these variations, but much is going to happen to the landscape. You see, we barely see any variation in the landscape. Okay? Is do what Sebastian has told us we should do. We should look at the input, plot the input, and plot the output. And we get different outputs for this. The first thing we want to look at is the flux coming out of this. This is a so easy to compute. I'm not going to go into details, but what I'm doing is I'm calculating the mean topography of my landscape. It changes from time to time, or the sum of the topography, and I look how it shows to the next. If it doesn't change, then I know that the flux coming out of this mountain is exactly equal to the tectonic product of U, the uplift rate, by the size of the model. If the topography changes, means that being more or less than the steady state tectonic flux coming out of this. So this is one way to calculate the flux. And I'm going to do all this computation. I've done some, and it takes, you know, it's not super slow, but it's a bit slow. And I'll show you in a minute a way to be efficient. So what we do then is we have computed this flux, and notice that I have divided it in flux, which is the uplift rate times the area of the model. Okay, so let's now plot this, and this is what do we see? Well, we see the orange curve is the precipitation. Okay, so and then at some point it starts oscillating like this. Now let's look at the flux coming out of the mountain. Well, at first the flux is negative. What does it mean? It means that, you know, when this flux tends towards zero, it's that steady state. So this flux that I'm plotting here is the flux minus the tectonic flux. Okay, I realize actually that this is not really helpful this way. It might be easier if I just calculate the total flux coming out of this. You know, you'll see in a minute why I want to do this, and I'm going to so basically calculate, rather than calculate the flux or in subtraction of the mean flux, I'm going to calculate the total flux. But to do that, I need to know the erosion rate at every point of the landscape. And you agree with me that if I know the erosion rate at every point on the landscape, I can do all these avoidance, and I will get the flux of material coming out of the system. Okay? So for this, I have first to tell FastScape to give me the erosion rate. So, you know, if you look, you know, we could do this. Let's do it the way it's supposed to be. I'm going to add a cell here. I'm going to look at the model called SPL model. So if I look at a SPL model, there is one of the model called erosion. Processes called erosion, and in erosion there is an output variable out, which is called rate. So I can ask my to tell me about, you know, to exit erosion rate. And I remember when you put it there, this is a convention in Python that I don't fully understand. You have to do it by putting 2 underscore. So it's erosion underscore underscore rate, and I want to get that at every time step. Okay, FastScape again, asking it now, give me the erosion rate, and then I'm going to calculate the flux coming in out of the model, but by using this erosion rate. So let's look at the erosion rate. Because I've FastScape computed this out does ds dot out, okay, which is the output of the model. It also has the input, and you see now there is this erosion rate, sorry, here, erosion rate that I have computed. So let's look at the erosion rate. Let's go on this crate. This has a lot of numbers. Why? Because it has a dimension of x by y. So there is a point in every node on landscape, but it also has a dimension of 201 time steps. Okay. So what we can do is simply do the sum over all x and sum over all y. Okay. And if I do that now, I have an array that's of length 201, which is the sum or mathematically we can call it the integral of the erosion rate coming out of the model. And I could do even faster by asking to do a mean, which is almost like a sum. And the mean is actually doing the sum and it divides it by area. So this is what I want. This is actually the mean erosion rate. So if I multiply that by the size of the model, I will have the flux. Okay. So if I now multiply this by the size of the model, and the size of the model is S squared, I now have the flux of sediment coming out of the model. Okay. So I'm going to plot this. I'm not going to bother dividing that, but I'm going to scale it by the uplift rate, by u that I'm in there. And you do that, the steady state value, okay, so if I take the mean erosion rate and I scale it by the uplift rate, mean erosion rate at steady state, you see that my flux tends towards 1 when I'm at steady state, and then it fluctuates around that. So let's go and remove, okay, I'm going to simply cut it out. I have the original somewhere. And I'm now going to use for the flux this. This is my definition of the flux. And you see, it is still one of the, well, let's just look at it. So if I run this now and ask me plot the flux, now I have the precipitation here and I have the flux coming out of the system, okay? I should, and it will be even better. So now I can see, okay, the variation in precipitation and the variation in flux. And that's by the mean precipitation and normalized by the mean flux. So I can compare with an apple. Zoom on this region here. So I'm going to ask only to see, I'm going to reset the axis of my plot, which I think is something like this. And I'm going to go from my, what I call T equilibrium to T final. Okay, so I'm going to look at, oops, set X lim here. So only look what happens after steady state. Okay, so from 10 million years to 10 million years plus 500,000 years. What do I see? I see that when the precipitation increases, the flux increases. And I see that the flux decreases. Why? Because in the stream power law, very simple, the erosion rate is proportional to the precipitation. But remember, the erosion rate is proportional to the precipitation to the power m. Remind you, here we've used m equals 0.4. Okay, so we're looking here at the precipitation and in terms of flux. And you remember, Sebastian told us something very important. What we must study first is how much of outgoing signal, the sediment flux out of the mountain, as a function of the amplitude of the forcing signal, which is the precipitation. That we have a mean precipitation of 1, And I have imposed variations that have an amplitude, if we measure this amplitude, between 0.5 and 1.5. So let's call my amplitude is 50%. Let's look at the flux response. It's smaller, okay? It's less than half input signal. Let's look at, we can actually quite easily compute the amplitude of this, amplitude of the view. And what we find, okay, so I should just, I'm going to put so it looks cleaner. It's something to do with this being, whoops, I shouldn't do this, obviously. What have I done wrong? Doesn't matter, I'll leave it as it was. It will print it in a funky way, but okay, let's look at this. With signal forcing, so peak to peak of the forcing is 1. Okay, it's 50%, but it goes peak to peak. And we get the of the flux is 0.416. It's actually roughly 0.4. Because the erosion rate is proportional to the precipitation to the power n. And therefore, the amplitude is scaled down by this factor m. Let's just check that, okay? So you can do it. I'm going to let you work in a minute. So let's do this and run now with m equals 0.8. Then I multiply n by 2, that the ratio, I'm not going to change the concavity of my landscape. And I know I've done it a lot of time, that to get a normal mountain, I don't really need a mountain, only a few thousand. When I change m and n, I have to also change kf to 10 to the minus 7. Okay, so I'm just going to run the same model. Okay, same input, everything is the same uplift. I'm going to run it. We can look at it again. I'm going to calculate the flux. I haven't changed the amplitude of the prism. So we could look at it. We don't really want to do this there now. And let's look at the solution. This is what look now. And we see that now the precipitation are different. Why? Because don't forget, I'm sorry, it's still 1. No, sorry, didn't run the scale. So what we see now is the precipitation signal is the same, you know, an amplitude of 1 peak to peak. Now, the flux coming out, the amplitude of the flux response is much greater. If I look at the ratio between the two, so we see that the output signal, the flux that I get out of this, which is what I'm going to record in my Sediment stratigraphic record, scales with the precipitation variations. They increase when the precipitation increases, but the amplitude of the signal is controlled entirely by m, the area exponent or the exponent. We all get that? Any question on that?
I have a small one. Do what you did on the last cell. I don't have the answer for
what?
For the last part. Like you had like 0.4 or something like this, and I don't have anything.
This?
Yes, sorry, 0.8. I don't have this one.
Oh.
I just have forcing.
It's for shown.
And I actually tried to do everything like you, so.
So all I do, you see, is this means that I look at the flux from, this point, because it's a flat curve, huh? Okay? So only go from this point, this is what this mid 2, so only start at 1 time step. And I'll see minimum value. The difference between the two, I said, is the amplitude of the signal. I do that for the flux and the forcing, and then I just plot the. So, sure why. We'll come back to it if you want. It's simple operation.
Okay.
Should work. Now, what I'm going to ask you to do now, so with this, with a very rapid signal, let's play God, okay? And let's make it now a million-year signal. So rather than 100,000 years, it appears 1 million. And I ask you to run it, and we're all going to do it together and see and look at the answer, okay? So let's do this. So now you see that this is a longer signal. Let's run the model. It's cool thing, if you've commented on this story called Z group, it should run quite fast, like it is for me. Otherwise, trying to write disk and it doesn't, it's slowed down by the writing back to your own disk. Don't have to display it. We can look at it, see what happens now. No, let's just look directly at the flux. So we don't, I calculate the flux, and now I plot the result. Okay. So can you describe to me what you see? To help you, I'm going to put a horizontal axis.
The amplitude of the flux is increasing?
Sorry?
No, the amplitude of the flux is increasing?
So the amplitude is slightly decreased. I was pointed, but I'm going to put you something that might help you. So I'm going to put once. I'm going to draw a straight line. That's the observation.
Of the bottom is the amplitude of the bottom is higher than the.
Exactly. The curve becomes a circle. Okay, it's tail and fail, like it follows the precipitation. The amplitude is a little bit decreased, but it's decreasing more precipitation. I should get more flux, but I don't get as much more. Then I get less. This here is relatively smaller than this compared to that. See, this sine wave, the blue one, is deeper negatives than positive mountains. Okay, so let's put them down on our notebook and let's run it again with, let's play God. Let's make it a 10 million year cycle and run it, okay? So my extend have these long 10 million year cycles. Let's look at the flux. Things are getting really strange now, okay? What has happened?
They gone out of phase.
It's getting out of phase, that's the first thing. And it is getting like that way now, okay? So it looks like things go fast and slow. The flux coming out of the basin is increasing very rapidly. When I increase precipitation, it's slowly when I decrease precipitation. And there's an offset. And let's one more time play
Sorry,
God.
sorry, John.
And
First
do-
question. It's in
Yes,
the
yes,
figure
yes.
below. It's why
This one?
precedes precipitation. Wouldn't be more natural in the opposite.
Very good observation. Isn't that strange? It's guessing the change in the future. You're exactly right. That makes no sense, does it? Very good observation. Let's write it down on the notebook. We're not only out of phase, but we're behind it. So no, we are in phase. If time flows this way, the flux increases before the precipitation rate increases. All right? So let's scratch our heads and start to think, look, in most geological cases, you don't know the orange curve usually. What we know is the blue curve. We record that in the basin. And so if you think, like we did for the very rapid variation, that is a measure of precipitation, we start to be in big trouble here.
But couldn't it be
very late?
the particle of precipitation?
Physically, it must be. You're right, Melanie, of course.
Okay.
The basin doesn't know what the climate is in 1 year. Hopefully, otherwise, we should turn into philosophy or theology and not geology. Okay? Point, Melanie. Okay, let's play God one more time and let's push it really, really tough. Now we're gonna make a cycle 1,000 years. Sorry, where was I here? What have I done here? I thought I changed this. What's happening here? Let's see. Am I? Oh. So these cycles are, should be 7, didn't I? I wrote 7. Yeah. Oh no, that was 1 million years, sorry. So there was 1 million years. So now let's make it 10 million years. Sorry, I'm myself. Something strange here. I'm getting old. Anyway, so let's even increase more this and look at the flux. And that's what we get now. I think that's completely, squeezed that way, but also the amplitude is very much decreased. Now, if I was a sedimentologist and I believe there's been some climate change there, okay? Look, this is a big change, changing precipitation by a factor 100%. And there's nothing almost coming in terms of variation of flux. So most likely in the real world, the precipitation, the amplitude is going to be much smaller than what I have assumed here. So therefore, the signal coming to the basin is going to be undetectable. One thing accessible to me that, even if I had a superb stratigraphic record and a superb set of, dating techniques, whatever they are, I just managed to actually see that in the field. So the signal, as far as we are concerned as geologists, is completely gone. So why do you think, this is the last observation, why do you think now, when I'm forcing this system at a period of 10 million years, no, I think, is it 10 million years, yes? Just nothing, I can't see it. Even though, my mountain, and let's look at the mountain. That's very interesting. Let's see what happened in the mountain now, looking at the topography. Okay, so let's play the movie now. We are growing state. We're going to reach steady state. Here we are. And now let's go and see what happens to the topography. Wow. Look, can you see it?
Mm.
Can you do this on your massive changes in topography? So, you know, if I have a GPS running for 10 million years on top of that mountain, I would see a massive signal, the mountain going up and down and up and down. Yet, at the bottom, I'm waiting for the sediment to come and nothing changes. So I'm obviously playing you, okay? What's the solution? But just to make the point that even though we are using law for erosion in a mountain stream power law, which we know works quite well to reproduce all sorts of things, at least at this scale, compared to what I put in is totally unpredictable. If I have very, very rapid ones, if the variations gets too long, it just kind of breaks down. When the variations are very, very happening, it doesn't change. But the flux completely changes. If I have very long variations, that varies a lot, but nothing's changing in the flow in the sediment. All right. So scratch your heads. I'm giving you 5 minutes to figure this out.
As we have very slow variations in precipitation, I think that the system more state. So it's always almost at the steady state, even with variations in the topography. Then stop the variation of precipitation, and with time they will reach the steady state.
And how is the system always trying to get at steady state? What is it trying to do to stay at steady state? To match the tectonic is
adjust the base level in the foreland basin so that it's only the ratio to get to base level keep up time.
We'll see that tomorrow when we have a basin, but here there's no basin, you know, we're just looking at what's coming out, but there's no base level here. What's changing here? When I play it, the second part, what's changing?
The elevation, the topography.
Elevation. And why is the mountain going up and down? Any way it can contain the steady state flux, if you change the precipitation to maintain the erosion rate at steady state, it has changed slope. It's the only way the mountain can adjust itself to maintain an erosion rate that's equal to the uplift rate. Is changing, it needs to change the slope so that the product of the two remains constant. And so the system goes down, has low slope, and when I have low precipitation, the system must grow to have high slope. Let's prove it ourselves. I'm going to plot another thing. I'm going to plot here, and I think I can do this because I've done it before. Let's do it step by step. I'm adding a cell here, and I'm going to look at DS out. I have topography and topography 2. So topography elevation is again a big, you know, okay. I can look at the max value of that. Specify that I want to do the max in space, not in time. Or it's actually better because the max can be, let's look at the mean elevation. X, I think it's a better way, and the mean in Y. Now I have a time series of the mean elevation of the topography. Okay. Let's call this topomean. And now I can plot it. Okay. But let's, okay, so here I'm going to say AX plot Tim mean. I'm going to label topomean. Okay. Now the problem is that the topography is a compared, so I'll scale it down. Okay. So I'm going to scale it by topomean. Again at 101. 101, okay? So it will converge to 1 at steady state, and then we'll see the variation compared to that, okay? So now if I'm going to remove this so we don't see it, and I plot it. Now, mean equals this, and I plot it. Now I get everything on the same scale. Okay. The top green curve is the mean topography scaled by the mean topography, at the end of the steady state phase. So what we see that when it rains a lot, let's take a cycle here in the middle. When it rains a lot, the mountain decreases topography so that it's trying to maintain a steady state flux. And as it rains less, the mountain grows less erosion until it tries to reach new slopes, bigger, steeper slope, to compensate for less precipitation to steady erosion. So that erosion, as you said, Ariel, remains almost constant. There's very little variation. The heat, the is all equal to the tectonic flux. And so the mountain, from a sedimentary point of view, becomes totally irrelevant. We don't even see precipitation. All we see is the flux coming out of the mountain, the tectonic flux. Okay?
Is the topomean slope topomean, you think?
Yeah, actually, if you want to get into the details, it's really fascinating because, and I can show you this. It's topography. We look at erosion rate in the mountain, okay? And if we rescale it, so if we play erosion rate now, I'm going to show you, you see this wave of erosion until we reach steady state. Hopefully that point's coming here and the land trying to get to steady state. There we're almost there. And now, it doesn't show well here, but actually the way this can react is by propagating midpoints. This is the only way a mountain can propagate. And so what you have is waves of erosion. And so it's getting even more complicated that depending on where you look in the landscape, you will see the topography, not really reacting as it does. So let's take the mean, takes away all these variations, and it's a reasonable good measure of the mean topography, the mean slope, as you say. Now, just to understand what's happening, the case which shows really bad is the previous one where things seems to happen before. Okay, so let's go to a million-year cycle here and run it again, and let's look now and try to understand what is kind of behind the precipitation, or no, sorry, ahead of the precipitation. It seems to know here or next million year. All right, so we have 3 curves now. Let's try to understand this. Let's follow the precipitation. Okay? When it goes up, let's look at the topography. Topography seems to be higher when it rains less and lower when it rains a lot. But it's there, but it's a bit of, it takes some time to get there, okay? So it's slightly offset. At maximum precipitation, reach the minimum in elevation. I'm gonna try to, but I'm not there yet, okay? So there's a slight delay between these two. Look at what happens in terms of sediment flux now. Well, to understand the sediment flux, we must look at the topography. When topography is increasing, or more exactly, when the topography, it's easier to see it that way, while it is decreasing, it means to decrease the topography, I have to erode more. Okay, I have to here. I have to erode more than the tectonic flux. So while the topography is decreasing, the flux out of the mountain will increase. And you see that while I'm decreasing the topography, the green curve here, so I have a positive sediment flux anomaly. But as soon as the sediment flux, sorry, the topography stops and increases here, then the sediment flux becomes negative. That the sediment flux is out of phase, but close exactly the topography. And the topography is completely out of phase with the precipitation when I have high topography. So it all makes sense when you think about it in this way. But if you just look at the sediment flux versus precipitation, it just makes no sense. Okay? Now, this is happening.
Next comment. Sorry for that. Sorry for interrupting you.
No, please.
This is all this considering period precipitation change, isn't it?
Yeah.
And at some point that during higher precipitation course, the grain size is
yes. So the grain size information, this is what we're getting into. The grain information become a better tool or an additional tool that allows us actually to see these things, even though there is no variation potentially into the sediment flux, or even a variation that is really hard to interpret. Right. This ending now, this is her PhD project, in putting a grain size model into this, so that we can actually predict the grain size and see what grain size. Otherwise, just showing here, it's very, very difficult. If you only rely on volumes, on sediment fluxes, you have to be very careful to interpret this. But you made a very good point too. You said the word that I wanted you to use, slow or when it's fast. And the big question is, with respect to what? I just, well, a million years is slow, or 10 million years is slow, but you believe me, okay? The question is, with respect to what? And it is actually, we discussed that briefly yesterday, with the time it takes for the mountain's slope, that's the key, okay? And Sebastian introduced that notion to you today. It's what he called the time of the mountain. It's the time it takes for it to actually react by shape in precipitation. And to estimate that, a good way we could do it with the model, we just run a model and stepwise precipitation. And we should see how long it takes for the mountain to either go from low to high topography or high to low topography. There is, I've done this for a living for some years, there is an analytical solution for this, and it's there. Okay. And we can compute this. what have I done? It's not working anymore, so I'll win this. We get this from this theory, and we get that for the uplift rate we are using, for the AF play a role here. Basically, our mountain, the one we were looking at, has a response time scale of 1.1 million. And that explains exactly what we see here. We understand that if we have a cyclic variation that's near, we get in trouble. Everything gets out of phase, the amplitude decreases, we might not even see anything. But less than a million year, we can see them beautifully in the sediment flux coming out of the mountain. And we also know that the by the amplitude of the response is M. It's the area exponent in the stream power law. This is now a sedimentary record, like for the Pyrenees, and I want to say, is this signal indication of something happening? The first question I have, what is the response time of the Pyrenees? And if the signal that I see is of that time, longer time, I can say, it's not climatic, or if it is, it's a big mess to interpret. But if it's much faster than the response time of the Pyrenees, then I can say, there's a good chance it was a climate signal. Models, are just models. It's not a real mountain here. It would have been a mountain, okay? But they have the advantage that, we think the stream power law is pretty good. I mean, just erosion rate proportional to precipitation and slope to some power, which, must be really true at the scale of a mountain. And if we can then this behavior we have to be very much aware of. So I strongly advise you to play with N period again and back to Diga, because this figure is really one we need to scratch our head to understand how it works. And the sedimentary flux is not like predicting what's happening in the future. The sedimentary flux is this much behind. Is this much behind, so following the change in precipitation, because first it has to respond to topographic change, and then to that. So it's because it has to go in the show mountain that it does that. Let's quickly run again the other extreme case. Run the fast 100,000 cycle climate variations, and again plot this figure. We know that in that case the mean topography, where is it? I can show it where it show it to you by putting circles so that we see it. This is the topographic signal here. There's no change in topography. The mountain has no time to this rate change. So the mountain is the same height all the time. But the slope being constant, now erosion rate is changing a lot because I changed the precipitation, but I can't adjust the slope. So in that case, the erosion flux is directly proportional to the precipitation flux or the precipitation variations. Okay? So play with this. I have another exercise, which I'm not going to do today. I'm going to simply tell you to do it. Is to go to the next notebook, which there is a if I can open it, which is very similar to, why doesn't it want to open? Open, here we go. Okay, except that now, and I'm not going to even run the cells, rather than having change in precipitation, we're going to assume a change in tectonics, in the incoming flux. And I'll play it like we did. Look at the solution in terms of flux and tell me, analyze how is the sedimentary flux and the height of mountain responding to a change now in tectonic flux, in U, you know, the uplift function that I've put in FastScape. And we can maybe start discussing this tomorrow morning when we come back together again. But I won't do it today. I went too fast, or are you happy with this? It's really an illustration of really what we call signal processing. This is really almost the core of what we would like you to understand coming out of your PhD and be familiar with. And I really like someone saying, no, what about grain size? You know, what about chemical weathering? What about whatever? All your PhDs are coming into this. And remember, we have classified you into, you know, rapid, whatever, okay? This is exactly it. Some of you are going to work on anthropogenic changes that happens on the year scale. Some of you will work at the peak scale, a few tens of thousands of years. And then some of us, you know, or you will work on the long-term mental dynamics beneath Africa. This is all of it is here in these two notebooks. And we're going to take a break now. And when we come back, we're going to see that things can even, when we look at the basin now, because the basin will receive the flux we just talked about. And often doing stuff, but for those of us who are going to use the marine record, it's going to give the signal it has received to ocean and will transform it again. So we already have now, by the time it gets into the ocean, we've had two machines that have climatic signal and potentially the tectonic signal in ways that are not trivial and complex to understand. That will depend on, of course, the parameters of the model or of the process, you know, K, M, and N, but much more importantly, on the period of excitation and nature of the forcing, climate or tectonics. But let's come back in 10 minutes, and we'll have another, you know, 35 minutes left to look at the. So we'll see you back in at 4. You know, if you were not in the Docker, it doesn't matter. I sometimes like 100 nodes running at time matter, but because we're on the Docker is only allocated a small amount of memory from your computer, and then
Jean?
it just saturates and then
Sorry.
it just. Okay? So
if we
yeah.
go to kernel, the above, is it the same?
The kernel, there's a kernel running for each notebook. So the other thing you can do, interrupt kernel or down kernel, you can do that, but only when you have selected and you are working in a notebook. So if I reopen this one, okay, kernel, shut down all kernels, okay, that will turn this kernel down. You see it stopped running. That's right, Karen, you can do that.
Okay, thanks.
Notebooks, and let's go into the basin transit, okay, the second part of the S2S system. Let's open the first one. So you know the little picture has changed now. I'm showing you a figure of the famous, forgetting the name of it. Oh, gosh. Anyway, it's on top of the Aquitaine Basin, this big mega fan. Merci. Write it somewhere down, François.
I think when you
Okay.
get your mouse on it, you'll see it.
Thank you. And I actually typed it in so I would remember it. Thanks, Caroline. Amazon fan, okay? The mega fan, which is very large, as you can see here. Because now we're going to try to model that the system. We're going to try to model independently of the mountain. So we're going to have to play a little trick here, okay? So some basic equation. Now, all we know so far is the stream power law here, which tell us how rivers in size. One way to improve our model is to add a deposition term. And you can see it's a deposition term because it has a plus sign. Okay? So minus decrease topography. This one is going to increase topography because it's positive. Okay? Now, this is one way to do. It recognizes the fact that even when you are in a basin, you can be at some time eroding, at some time depositing. An avulsion in the basin, and your river that was depositing is deposited so much now that it can't flow there. It's too high. It's going to switch there and erode a bit before it actually starts depositing again. That's what avulsion do. Okay, but you could also be in a situation where you're subsiding a basin, and then there you deposit to fill the gap. Stop, and suddenly your river starts incising in it. Okay, so we want to have a model that is able simultaneously to erode and deposit. The way to do this is the so-called transport limited approach that Sebastian has mentioned to you, which is the Diffusion equation. I'm not going to go into details of this. The advantage of this approach, which is to use the stream power law plus a deposition term, do both. If you're in a system where, you know, uplift is really, really, really fast, you're never going to deposit, and you'll have the pure power. You are totally in a detachment limited system. If your uplift rate is very low, or you're not to erode, the uplift becomes subsidence, then this term is never going to play any role. You're purely depositing. You're going to be only in this term, and you will be in a purely transport limited system. So the advantage of this equation is that it can naturally model both the detachment limited problem and the transport limited problem. Okay? So again, I'll give you some equations here. This is what we've put in FastScape. So all we've done is added this term, which computes the sediment flux and says we'll deposit if in proportion to the sediment flux. And what is the proportion? The proportion is a constant, like another constant, we call it G, and we divide it by the drainage area. In fact, it's like here, the drainage area proxy for charge. The stronger the discharge, the longer it will take for the sediment to deposit, and therefore for a given sediment flux, the less I will deposit. If my discharge is very slow, then sediment will be able to settle down in the river and it will deposit much faster for a given sediment flux. So this G over A tells me how much of the sediment flux will be deposited or not. Okay, so you see there's two ways I can deposit more: by decreasing the flow in the river, decreasing A, or by increasing the sediment flux. If I increase the sediment flux for a given G and a given area, so much sediment and I need to deposit, I will go beyond the transport capacity and I deposit. Okay, so it's a very neat way to do it, and this was developed by it's a really important paper to read by Davy and Lag. Okay, and with all the equations in this paper by Davy and Lag, and with Xiaoping Yuan, postdoc in my section, we have actually developed a method to solve this equation again in order n and fully implicit, which it means very, very efficiently. So you will notice when we put the sediment in FastScape, it starts to slow down a bit, but it's still super fast. Okay, there's a bit extra computation needed, but it's fast. Now, the last part here, I don't want to get into this in too much detail, but it's comparing this to a diffusion approach. All I want you to remember is if, again, I look at the steady state solution for this. So I have a plane, okay, like a Holland, okay, and suddenly I come with a very big river that's coming out of a mountain with a constant sediment flux. I'm going to pile up the sediment on the plane, and the sediment is going to come out at the other end in the ocean. At some point, the flux that's coming from the mountain will be equal to the flux coming out of the ocean, and I will have built a sedimentary fan, a sedimentary system. According to that equation, I can predict steady state. When everything has reached a steady state solution, I can calculate the shape of that fan. Okay? And it's telling me, oh, look, I put this to 0, I have again a relationship between slope and area. Like in a... And from that relationship, I can just guess what the shape of the fan is by integrating it. Very, very similar to the slope area relationship that we derive from the mountain. The big difference is not m, but it's m+1. Minus m over n. Now it's m plus 1 over m. And then this now, instead of having u divided by k, it's gq as 0 divided by kf. Okay? So there's a big similarity. It's going to produce a similar profile than in the mountain. But of course, the height is going to be different. It's controlled by something else. Interestingly, if you take, which Sebastian will introduce tomorrow, by saying that, like he did already started to say that the rate of topography sediment system is due to the variation in space of the flux, and the flux has this shape. Okay, so this is the pure diffusion sedimentologist approach, which is a very different equation from this one. Okay, a very different equation. You can take of this, nothing to do with this. Yet, when I take it to steady state, I look at the steady state of that. I get this relationship, which gives me this relationship. And what I get, I already also have a relationship between slope and area, and the power here, which is the one really that is important, that determines the slope of the log area versus log slope. Okay? The one we did yesterday, is the same. And the shape of the mountain is, of the fan is the same. So even though we have very different equations, the steady state solution is identical. And that's why, with sedimentologists and tectonophysicists, or geomorphologists, we've been arguing forever, this is the right equation. This is the right equation, said geomorphologists. All we have to do is add a term like this, and we get the right shape for the fan. And the sedimentologist has never been in a mountain, says, no, we have to use erosion, which is what we've always been using in sedimentary systems. We don't care about erosion in the mountain. And we get the right shape for the basin. We get the same. This bizarre thing, not bizarre, there are mathematical reasons behind that, that by using two different equations that come from two different fields, we get the same steady state solution. But what is important is that the transient behavior, the way this equation responds when we change precipitation or change uplift, so not the steady state, are very, very different. Okay, so this is getting into a bit of the details, but you have to remember that, that diffusion equation and the we call it the reaction advection equation. This one lead to the steady state shape, but totally different behavior when we perturb them. And so you can ask me which is the good one. I tell you while you tell me. There is no definite word that will tell us at this stage which we should use. Okay, and maybe at S2S, we will have the solution. This is something we should definitely, I'm happy to work with any of you on this problem and think of ways we can actually, by looking, obviously not by looking at models, that we're going to get the solution to this problem. Looking at observations, decide, yeah, this definitely applies more than that one. Okay. Again, there's a theoretical time scale you can derive of this. We're going to play with this. Okay. So let's now the theories do it with FastScape. So let's open the second notebook and sedimentary model out of FastScape. Okay. So I'm going to run this. Okay. And then there's which is called in FastScape sediment model, which actually solve this equation we just talked about, but also has slow processes in it. We talked about now, okay? So the first thing we're going to do is like we did last time, we're going to take the sediment model from FastScape and we're going to remove the diffusion, add the hill slope diffusion to it, okay? So that, and then we create a new model, which I'm going to call the transit model, okay? The model again, okay? So you run the notebook cell and it gets very complicated. Let's just go, I think, input, true. Missing thing. Of course, it has inputs that we have to deal with, okay? What is it that's so complicated? Well, it's exactly the same as the Strong rule. This one parameter is G. But we have the problem too now that we have both sediment and bedrock. And, erodibility of sediment. Whoa, sorry. I don't know how to undo this. Oh, gosh. Sorry. Must be, but I never find. This is so frustrating with Safari. It increases when you do something with the mouse. It zooms on the thing and then you can't get out of it.
Maybe clicking Ctrl minus can go back.
Yeah.
I don't know. No.
No. Do it again. No. Ah, thank you. Thank you. Thank you. But it's limited. Doesn't go down as far, but not as much as I wanted to. I'll go further than that.
When you do the pad with two fingers on the pad?
The pad works. I don't want to see the pad. I need to open my computer and then see what's going to happen. Everything is going to go. Hopefully, Zoom doesn't like me when I switch from one screen to two screens. So let's try again. And now I can do this. And try again. And see if Zoom is happy with this. Right. Can you still screen?
Yes.
Good.
But now the size is very small.
Yeah, I know. Okay, can you see?
Yep.
Okay, good. So the is that we have both sediment and bedrock because we're going to deposit sediment. So the K and the G have two values for bedrock and for sediment. But we're not going to make, do that difference now. We're going to just have of course, play with that later, but we'll always put the erodibility and the G transport coefficient be the same for both. Okay? So again, we're going to run a simple model here, which has 100 kilometer boring now. 101. I'm going to assume a constant uplift, U0. Yeah, what I'm going to do is I want a very simple, only a basin, okay? And I'm going to assume first that there is no subsidence in the basin. So it's just a plate, you know. I'm going to pour sediment and see how it piles. I do this so I can compare the solution to the analytical solution we have here. Okay? So this solution. So to do this, what I'm going to do is, I think the best is to show you what I've done here and show you in the diagram, but only along one side of the model. Okay, so it's like having a very, very narrow mountain purpose produce flux, and then the rest of the model is going to be no uplift. So this is what I'm doing here. Okay, so I'm going to feed this to FastScape uplift rate here. I'm going to put, you know, we've used these boundary conditions, looped, to have a cyclic one boundary, a closed boundary. So the closed boundary is where I will have the flux coming from. And then the fixed boundary is flux is out. And you see nx by n, y by nx, yl by xl. Okay, and there's an extra explain in a minute. But we take 0.4 and 1, and then as I said, the erodibility 10 to the minus 5, and we're going to assume that it was 1. I've actually written a paper with Jean-Ping, but also Laure Guérit. Sebastian mentioned her name earlier. She was in the program project that we run until, or still running, but it's finishing now. And what Laure did was to actually, Jean-Ping's advice, there's actually a simple measurement you can do when your sedimentary fan is at steady state to measure in the field the value of G. And she went into, you know, tens and hundreds of sedimentary fans around the world and measured the value of G. And she found that almost everywhere, it's highly variable, but there's a mean value of about G between 1 and 2. So going to G equals 1 is a good way of representing sedimentary systems. If we do that, let's run this. And the model. So you see, it's slightly slower, okay? It's a bit more than a second this time, because it has to be seconds, so you get with the sedimentary flux. And look, I've asked to look at the topography, I have asked the model to output the topography and drainage. Let's do that. Oh, it comes in black. I don't like this, so I'm going to put light gray. Okay, and so this is the last time step, okay, that I'm looking at. So you see I have this fake mountain, which is simply producing sedimentary flux for me, and then I have a basin here, but I can't see it very well, so I'm going to increase the vertical exaggeration, okay, because the basin is only, you'll see, maybe 100 meters thick. Huh? This accumulation of sediment that I've put, the sedimentary fan that I've created on this flat plane, is very shallow. Okay? So I play, it's not very exciting because we're just depositing sediments, okay? But what's interesting is that real fan, okay? We know that, you know, stuff is not going simply to be deposited like a pile of sediment. It's actually going to happen because there are also rivers in the sedimentary basins. But these rivers are much more unstable. They are in, you know, in the mountain. They can jump back and forth a lot. They can go through what is called avulsions. They're going to deplete, fill their own bed, and then they can't go more. So they'll have to switch, go somewhere else where they'll build another little levee and build their own bed and switch again. And we found a way to reproduce this in FastScape by not using the single receiver algorithm. I'm going to go now, I don't want to do this, but quickly, maybe I will do this. Go back to the very first notebook that I gave you. where I was trying to describe here the FastScape algorithm. You see, every node only has one receiver, can have more than one donor. Well, we actually found an algorithm that allows you to compute the FastScape algorithm. I think superfluously assume has more than one receiver. Let's say here that 0.2, 6, and 8 are lower than 0.6 receivers. 7 can give some of its water or some of its sediment flux to the various receiver nodes that are more, and there are more than one. It makes it a bit more complicated to try to track things and do things in the proper order, but we can do it. And what it leads to show you the drainage area, which in fact is the flow of water in the rivers. Okay, so this is the discharge area. I assume a constant precipitation rate. Drainage area is a proxy for discharge in the river. So now if we look at the cell system, is to see these rivers that go through these avulsions. They can, we'll wait till it stops at the end. They nowhere, it's like these rivers stops like this. That's because by eroding, they have created a little depression, and there's a lake that formed there. And the lake. But what you see also is that rivers, unlike in a mountain, rivers can only convert. So rivers, small rivers become bigger and bigger and bigger. But in a sedimentary system, the rivers can also divert rivers. Now, we have to be very careful that in FastScape, we don't have really a very strong physics to reproduce that. I'd be really confident that, for example, the frequency of avulsion is physically controlled by the model. I'm working on a paper that will demonstrate that it is a good approximation, but not perfect. So avulsions take place. The physics is not really derived from basic principles of avulsion system. Okay, but we can have something that really looks like that. So now let's look at this system now. Let's read this cell. What am I doing? I'm taking the topography elevation. I'm taking the last time step, and I'm cutting a cross section here. I look at the middle here, x equal XL. And I'm only to show you the result when, in the basin. So I'm not going to show you this thing here, which is what happens in the source area, which is irrelevant. It's this node that uplift. So if we look at that, this is what the profile looks like. And again, it's not very high, only a few meters of accumulation near the source, and it's 0 at the exit here. Okay? And we can also, have animation if you want, that looks at the topographic elevation, not the mean elevation, not in I selected one cross section. I'm going to mean all the elevation in the x direction. I'm going to plot this across time. And so this shows, the mean elevation, and I can show how the basin is going to reach steadily a steady state. Okay. And here you see also the source area is here. So I should again have put this condition to actually not show the source area. And the solution and blah, blah, blah. Okay, but it's just showing me that I do get, again, a very much power response that is very much in agreement with this solution, which tells me it should be a power law. Note, however, that to get this solution, I have to assume, again, Hack's law. And Sebastian has already told you that Hack's law, it works, but it's a very different Hack's law. The exponent, the p exponent is not equal to 2, is much closer to 1. Okay, any question on this before we go to the next and last notebook for the day. I'm just looking, you're still there. Again, please, play and see how it changes the profile. You'll see the concavity change. You can even play with it and make your concave way, which is not very natural. Doesn't look much like nature, but you can. Understand that because many sedimentary systems look like this, we have a way to actually the value of m and n, or at least the ratio of m over n again. So let's look at the next model. I want to do something, oh, it's not the right one, sorry. This is, I'm in, suppose this card, and I'm going to close this shotgun down, because I'm back to the basin transit, and let's look at this third notebook. I'm going to see your face because this is going to be difficult for you to comprehend if I talk to myself. One thing I want to do is look inside the basin. I'm going to make a basin, and I'm going to look at its evolution through time. But that if I want to look at the time of a basin, what I need to do is predict the stratigraphy. And in FastScape, we've built a module called Stratigraphy. And what it does, it remembers the position of the topography in the past. But that topography, without putting stuff on top of it, it gets buried. If you uplift something, it could be eroded away. So that's what it stores is the geometry of the topography in the past, like it would look today. So what I need to tell FastScape is, how often do you want to remember that topography? And these will be my stratigraphy that I will okay. Now, I was very lazy when I built this notebook, and I apologize for it, but it's fine. But I did something that is not really recommended. I forgot how to use the stratigraphic model. I didn't want to go back though, and I realized that the marine model always comes with the stratigraphic model. So what I'm going to do, look at this, okay? The model, you can have a look at the FastScape web page or whatever, what is in the marine model. I know what it is. And I move everything except the sediment model and the stratigraphy. Okay, so don't try to understand this crazy lie. Okay, but I'm building a new transit model that's based on the marine model, in which I've removed the diffusion. The marine model assumes some initial topography. I don't want to, it has a very special uplift model where things go up and down. I remove it and I replace it by where I specify a function that I define. I don't want to deal with marine sedimentation now, so I just remove it. We'll do that tomorrow. And the mean component, I'm not interested in sea level, so I remove sea level, which is another process, okay? So it's a terrible way to get access to stuff, but it's so lazy on the day, and I thought it was the easiest way. So now, again, my model looks exactly like a sediment model, okay, the one we had before, without diffusion, but with a little strati process here that allows me to do the stratigraphy, okay? And if I look at the input, I'll see that I need some input for the stratigraphy. So let's look at this. Here is the input to this model. It's exactly like the one we did, the sediment model, except that it has this additional thing here, which asks you, how do you want to store the stratigraphy? So how many stratigraphic layers do you want in your final model? How many, if you guys have used seismic sections, okay? The first thing you do is you take your seismic section And then you pull your pencil, your color pencils, and you're going to draw a reflector corresponding to this edge. And then you take another pencil, and that's a reflector corresponding to, these are stratigraphic levels. That's what exactly they are. And so what we do here, we predict and we store the topography, the surface topography in, but as it's going to be deformed and advected and eroded by all the future motion and erosion of the so this. And finally, because now I want to create a basin, I'm going to make still my little source there on one side, this one row of everything, but also going to make the basin subside. Okay? And this is this line here. Now I'm going to have a negative uplift. A negative uplift is subsidence. Okay, and I also make it with this geometry so that if I have an up, my source, my basin is going to subside like this. It's not going to subside like this, but it subsides like more like a fallen basin. Okay, so this is what I've put. And let's run the model, and let's look at the solution. So if I use again my visual 3D tool, well, again, this is a lot of vertical exaggeration. I'm going to decrease it a bit. I can look at this. I can look at the drainage area. Okay, I cannot in this 3D view look at the stratigraphy. I can only look at the surface topography. So it's still pretty boring. It's just the surface. Okay, it's looking at a basin, but I can look inside the basin because I only see the surface. So I need to look at the stratigraphy. And this we're going to use the plot. Okay, so let's run this. What are we going to do? Well, I'm going to look at the thing, stratigraphic elevation. And look at, I'm going to play it, it's better. Okay, so you actually see it. At the last time step. And what I see here are the topography in the past, but I have added stuff. Sometimes look at this layer here, the greenish, bad greenish color here. There's an unconformity here because that layer was sticking out like this, was deposited, but a channel came on top and eroded it away. So the stratigraphy is not just showing the topography in the past, topography plus the effect of erosion and deposition on top of it since it was deposited. And it looks even more if we plot it, in a plane that's perpendicular to this. So I'm making a cross section in the model. And what I see is that there is this channel that was active all the time, okay, to which the systems tend to come back all the time. And you can see it here. This is because I'm very close to the mountain front. It's this point here. You see, this channel active time. Whoops. Ugh. Terrible. I hit the wrong. Okay. Very active channel will always produce a very active river or channel here. And very stable, and it produces this behavior in the stratigraphy, which we can't see if we just draw a section here. So this is a very easy way with FastScape to not only create basin, subsiding basin. You see it's subsiding very slowly here. I can increase the subsidence rate. Let's do that quickly. So 2 10 to the -4, now the subsidence rate. It's a very fast uplift rate. So I'm producing enormous of sediment here. Okay, play it. And plot again now the profiles that we see. And if I look at the profile, now my basin is much deeper. Okay, it's 2,000 meters deep. I have this very enormous building sediment because I've put this very unreasonable amount of uplift here, okay? So I should decrease this to something more reasonable to get a reasonable. And you start to see here that, you know, the system builds this much greater, longer wavelength and conformity here. That Sébastien talked about allochthonous versus, allogenic versus autogenic signals. These unconformity are pure allogenic signals. There is nothing varying in the source. There is nothing varying in the precipitation or in the system. It's just random variation system that corresponds to these avulsions. And you see they can create what looks like, that's an interesting unconformity, an interesting erosional signal here. But cannot interpret that as a proof of something varying in the forcing. This, you can also notice that at this early stages here, okay, there were no unconformity. This looks very smooth. To the time where the basin was subsiding faster than you could fill it. You couldn't get to steady state. So you see positive here really fast, but you could not build much sediment in the basin because it was subsiding faster than you could try to fill it with the flow. Slowly, you pile enough sediment that you get to this situation here, where the basin is more or less filled now. And most of what's happening now is if you look at what's coming out here, during the early stages, there are very few sediments coming in. But we basically, in the sediment, in the basin, it's filled enough now that it's almost a purely bypass system, not get deposited. We used to have periods of avulsions, dominant periods of avulsion, where part of the basin is filled, part of the basin is eroded, part is filled, part is filled. And you create internal discontinuities or unconformity in the basin. Okay, you see, again, I'm not being extraordinary, but these little models allow you to see in real life, if you want, the life of a basin and start to, oh yeah, that makes, I know that, or to discover it. So I really urge you to play with it. Sometimes the model doesn't produce results that are really like this huge sedimentary pile here. But you know, we're not trying to reproduce every detail of the real world. We're trying to get the behavior of these systems, very simple systems. So I'm going to stop that, but just by hinting about what we're going to do with the four, and you kind of guess what we're going to do now, cyclic variation in precipitation rate. But not in the source, in the basin. And Sebastian asked the question, what do you think is going to happen in terms of transport in the basin if the precipitation varies? If we increase the precipitation, we can transport sediment much faster. So we're going to erode the basin. We're going to remove the sediment much faster than we can put it in. Conversely, if we decrease precipitation, it will be harder to transport the sediment and your basin is going to accumulate much more sediment near the source. Okay, so we'll look at this. I'm not going to do it now, but you're more than welcome to run these, look at the output and play with the source. Look at the structure side of this. The signal is stored into the stratigraphy, but of course, we're also going to look at the flux coming out and see, does it make sense or is it more complicated again? And play with the period of excitation. Okay, the period of the cycles. Good. So again, in previous courses, we want to show you so much. We tend to be a little bit more ambitious than the time we have, but I think we well. I would have liked one more day, more extra, but I will compact it a bit more tomorrow. And I think we will have had enough understanding of how things work that you will still get something out of it. But don't hesitate, you know, change the model, run it, play with it. If if you become sufficiently proficient with it, you can even go to the FastScape repository and play with the marine model, or there's many models we have this way to play. One that's exciting too, which I want to talk about, is the Flexure model. We talked yesterday about isostasy and flexure. They're to isostasy and flexure. It could be another whole course on that. I'm almost finished my little note on the isostasy. You should have. Any question, anyone?
Yes, I have one.
Yeah.
Is there a tool that allows us to see the stratigraphy in the dimensions?
Good question. Okay, so we're working on it, but you can still. I don't have the time to explain to you, but I'll say it in a few words. Okay, there is a tool called ParaView. I'll put it in the chat. Okay, let me reopen the chat. The chat should have appeared somewhere. Lost it. Chat. What is my chat? But anyway, let me. An action is worth 1,000 words. It's called ParaView, and I'm going to send it to everyone so you can see it. Okay, ParaView, and I'm okay. So can I do this? I think it's going to run. And it's not starting. Here it is. So here is ParaView. Okay, so it's a piece of it. Great for you. Otherwise, definitely install it. It works on Mac, PC, and Linux. It's totally platform compatible. Okay, you can just type ParaView download on Google and you'll get it. It's free and it's a 3D viewer. Now I can later show you how, when you have a model like the DS out, there is a function that exports the model into a file that ParaView can read. And in ParaView, you can look at stratigraphy in 3D. Okay, would take more than a few minutes to explain to you how to do it. Okay, but yes, we can do it. And I'm not sure I could easily find an example of that, but I with a bit of searching I could, but I will prepare it for tomorrow. I will prepare it for tomorrow so you can see it. It's really powerful. You can look at this as a 3D block. You can cut it. You can make sections. You can drill wells, synthetic wells. And on the stratigraphy, we store all sorts of things. So it's there. We can use it. But it's not available in a notebook. This 3D viewer that we are using, this one here, okay, is an experimental product that another company is developing, and Benoit, our software engineer, attributes why we have access to it. And Benoit is pushing for the ability to have more than one surface, like you are asking to put stratigraphy. But it doesn't have the, you can't force it on them, but it will come soon. Other questions?
I have one question. It's just a thought that I had when you show us that example state and the response for precipitation, how fast, for example, a fast event of precipitation will do a lot of erosion in the sediment flux. And if we did that in a very slow way, that does not happen because of the response. But what I'm thinking is that now think more short time, short range, is the extreme events of rainfall that we can have during a year. For example, we have suddenly very increasingly in our precipitation rates, and then the profile of the become more erosive, and then we have an increase of sedimentary flux during those extremes. But when we are regular charge, the profile is not in equilibrium. They are not ever in equilibrium, because when we have the extreme event, things goes. When we have a low precipitation, or we don't have precipitation, it's not in erosive condition. And what I'm thinking that will reach the sink of our system will be mainly, the deposits will represent the usual ones. I don't know if it makes sense to think like that, but it's just this the question.
That's what just extremely interesting and important. Okay, and I starting thinking about it in years whenever I first met with François, and we were looking at an outcrop in Brittany. You know, François was telling me, oh, these are individual stones, and I'm there. What? You know, we look at the sedimentary section. You know, these were things. You know, sorry, François, if I'm wrong, but very old, like the Ordovician deposits. Okay, so what the hell is this? I said, actually, a stone happened, you know, 300 million years ago, and if you can look at other things. You know, I don't know if you've ever worked on deposits from the famous snowball event. It proves that some of these deposits, that they are glacial deposits we have in the sedimentary record, to prove that they are happening on the beach. Okay, geologists use the fact that they are deposited on what they call rhythmites. Okay, and these rhythmites correspond to a core, okay, sedimentary strata of tidal action. So you see the tides, you see the daily tides, you see the monthly everything. And remind you, the snowball Earth is 700 million years old. So yes, it's incredible as it can think. We do record single events, sometimes big events, like what you're saying, you know, big storm, but even sometimes, if the environment is correct, we can record just all stuff that happens every day on the beach, every day, all over the world. So this is a big question. And there's a full paper, I think I can find it by Ganti. He's a really smart guy who works, you know, he's more a mathematician than anything. And showing that, you know, what do we record? And he assumes that the signal is not periodic like I'm doing, but it's a totally random process. It has some characteristics, okay? It follows some kind of the statistical distribution, but it's totally random. So there are event there, and also you have a big event compared to a small event. But it doesn't say anything about how they appear. They can happen, you know, too small after a big one, or 1,000 big ones before a small one. And what is shown there is that what you record, and most likely big is defined as the rate of subsidence divided or multiplied, more exactly, by the time between events, the recurrent times of your events. So it's basically, think of it, you let the recording tape go, will determine, you know, what kind of event you can record. And if a really random set of events, only record the events that you know have a recurrence time that's smaller, that's larger than the at which you turn the tape. That's your subsidence rate. I'm not very clear here, but basically it tells you that it's it really matters, not their amplitude. Mm-hmm. And so you can record very big events or very small events. It just depends on how they succeeded. Yeah. And of course, if you keep that in mind, if you have very big events and too often, the likelihood you can still record a small event, but because your big event is likely to erase the small event that happened before.
Yeah.
So it's not a perfectly clear answer. And to tell you how interested I am, I have actually, and you can do it, you're more than welcome to do it with FastScape. Rather than precipitation, like you can put a random series of rainfall events, big ones, small ones, and you can some of natural distributions that we think are correct.
Yeah.
The things that FastScape cannot do, I will finish very, very short-term events, because there are assumptions in FastScape that are not correct for the very short-term events. That in FastScape, the time it takes for the water to travel from the top of the mountain to the bottom, okay, that time much better than our time step. So we cannot see a single rain event and how it propagates down the channel. Okay. So that's a FastScape that we have to use other equations.
May I comment about the preservation of scale in the Strat record? So as Cécile mentioned yesterday, the time is not this in the sedimentary record. You have period where it's cadence missing and time where you get a very high preservation rate. And this is this period of very high preservation rate that you can get preserved scale, human scale even. So it means that in terms of prediction, we know quite well at which period you can expect to get preservation of such events. So it means that sometimes you can be able in 20 or 30 centimeters of sediments to have a 6 months record of the tidal activity. And a few meters above, in the same thickness, you can get tens of thousand years preserved. So it means that the geological record is a real yo-yo at different scales. So it's really something that you have to keep in mind. If so, you become a creationist. So we got trouble at the time we discovered tidal system with creationist people, because they use the sedimentation rate that you are able to measure on a system. And if you use it and if you extrapolate it to all the sedimentary record, you get Phanerozoic time, yesterday. So be careful about that.
Yeah.
Thank you, Jean, for this very nice course. Yeah.
Okay.
I have a. Jean, I don't understand the shape of the profile, of the depositional profile, because when we look at, I don't know, seismic lines, it's more sigmoidal than just that. No.
Which one? Sorry.
Well, the depositional profile was really steep at the beginning and then flattening, but when we look at seismic lines, it's more sigmoidal, no?
Yeah, I can, we will see that tomorrow. Okay, one of the issue, okay, is that the profile I showed you is assumed Hack slope. Okay, you remember?
And that's not for the catchment.
So I'll share my screen again. Okay. Let's have to do this here, and then go back to the Jupyter lab. I hope I still have it. Yeah, this profile. That's what you're talking about, am I? Okay.
Yes.
So this is a profile that I got to try to reproduce the theory. So I'll skip this here to reproduce the theory that I showed you. This form, okay? Mm-hmm. And I tell you, you get this by taking either, the classification that sedimentologists use, the diffusion equation. Both of them lead to the same predictive profile. Okay? That assume, as I said, is that to get from here to here is that drainage area obeys Hack slope. Okay. But here I have okay, that's the point. Now, in this approach, or in this, okay, I've made the model such that there is no mountain. Okay, I have a sediment flux coming here, but I don't have a big mountain. So what I have here is a sediment flux that I know that I'm posing. Also, the assumption is that the drainage area here is 0 because there's no mountain, which is saying that no water coming out of the mountain, that all the water that's transporting the sediment is water that's rained basin, which is not at all realistic, you understand? Yeah. Okay, so my transport capacity here is 0. I have assumed here that there's sediment coming here, a big flux, okay? But I've said this, just my mountain is maybe 100 miles. So there's no water coming up there, okay? All the water that's transporting here is the water draining in the basin, which is crazy, okay? In the real system, there is also water coming up. That's the water that's raining in the mountain. It starts in the basin, it already has a very large carrying capacity, and it doesn't deposit everything here. So tomorrow we're gonna make a mountain there, which will also give us water, and you'll see that the profile will look much more like you said, sigmoidal.
Okay, so that's just for the basin, and afterwards the. But
so what you will have is next to the mountain, you'll have a fan, a depositional system, and if your basin is very big, then you'll have a plane where it's mostly in transit, very little deposition, and you'll have a system that looks exactly like this. You see, at the foot of the mountain, you have this. Here, it's highly exaggerated because this is a mega fan. Okay, fan next, and after that, you have this plane where you basically transport by rivers that do not deposit much, like the. Tell me the name of the main river there. La Garonne.
Garonne. Garonne,
no?
Garonne, Dordogne, je sais plus.
Yeah, so you go into a system which is purely transporting. But, so you're right. Geologist, you picked out that this is a theoretical profile, but sorry, I've lost it. Doesn't really look much like a real profile. And the real sense to get to this analytical solution, okay, this one, we made the assumption that at the entrance of the mountain, or the exit of the mountain, there's no water flowing. But there, the drainage area is 0. Okay? There is actually an analytical solution if you take into account the drainage, a finite flux of water, but it writes as a very special function called an error function. If I'd shown it to you, you would all go, oh my God, this means nothing. But I will show it to you tomorrow. You'll see.
Okay, thank you.
Thanks. Any other question or comment?
Yeah, Jean, do you give us only tomorrow, if you need time to find it back, the paper you just talked about regarding what can be preserved in the sedimentary record?
I didn't find it yet, so I'll do that for tomorrow.
Okay, thanks.
I'm not going to sleep tonight if I do all the things I told you.
Would it also be possible to see the paper that talks about did a study on the values of G?
Yes. That one I think I can find very quickly. Let me just quickly do it. I think they should get it to me. That's a Jupyter. Yeah. So the best way is no Zoom. It's interacting with my clicks. There we go. Here we go. And I think I can even send it to you, even though I'm breaking every copyright law, I'm sure. Also sure you all have access. So I think now if I can reopen the chat, I can give it to you. It's this one. Chat. Here we go. Just my, well, I think I can do that, no? Yeah, so this is, you know, this value of G between 0 and 1 here. Let's see, it's geological data. Noise. I'll try to find again. Good. Thank you, everyone. Apologize for running over time, but I know these are very long days for you. Still, I feel so bad that we have to do this way. It's so much nicer to be, you know, doing it live. And we have the opportunity to get to be very pleasant. I've been part of other ITNs, and one that I really enjoyed was in the 15 PhD students. There was one postdoc, but 15 PhD students, and it worked really amazingly. All 15 PhD students interacted with each other, and many years after their PhD, they're still in contact and still work and publish papers together. So it happens too. It takes, you know, us to push you to do that, but mostly you guys who have to do that. And we know there's something. I don't want to take this make it too long, but one thing that really helped was that, you know, students invited each other to their own field areas. The student I supervised, you know, Eric Deal, you know, he was a geophysicist. I don't think he'd ever been doing any field work. He was a modeler. And he did go to the field twice, not during field excursions, but, you know, to help others to get a backpack or, you know, do samples and whatever. And that really helped for him to know all the others in the group. And that really helped everyone to interact with each other. So I can't force you to do it, but I think it's a great way to set up interaction. I'm especially saying it for Amanda and Pauline, of course. They don't have any planned field trip in the plan, okay? But I really hope that they will find the opportunities to go with you as often as they can. Good. Enough said. See you soon. I'll see you tomorrow, everyone.
Thank you.
Bye-bye.
Bye.